We cut and now reinstated, and you can see the total derivations for your viewing pleasure on the key or in the previous YouTube version.
Fletcher,
yes.
Did you say the other questions you thought were going to be on it as well, or were you just joking?
I'll put them on there.
Okay.
Okay.
Thank you.
Extra credit only. Okay. Okay, now where was I? We are galvanic cells. Yes, I knew it was something like that. If I can find the question. Yeah, this is. I feel like Bob Barker. Okay. A Winnebago. 2 Winnebagos. A baby's arm holding an apple. Okay. Here we go. Oh, this is the actual. That was the actual test. I don't want to do that. That would be bad. Okay, here it is.
We did the electrolytics. We're doing the galvanic.
We're doing the galvanic cell. So I'm going to erase this board. And it was Luigi Galvani. I just love Italian names. Alessandro Volta. Luigi Galvani. The galvanic cell, or the voltaic cell. Obviously heavily influenced by the Italian scientists. Now, okay. Given that the first question, let me eat my M&M, is which species is the anode in this reaction? What?
CR2.
The chromium 2 plus. Why is it the anode?
It's reduced.
Because it's what? It's what? Thank you. Yeah. Oxidation occurs at the and what happens at the cathode? Okay, so to answer this question, chromium 2 plus is the anode. That's A. Now B, given okay, this is all, I'm paraphrasing a little bit here. Given the reduction potentials for lead, So I'm asking what the standard reduction or what the cell potential is under standard conditions, given the standard reduction potentials for lead and chromium 3+. What do I do?
Cathode minus anode.
Yeah. So let's get that written down. That is, which one's the cathode again? Oh yeah, minus 0.1263 volts minus a minus 0.41 volts equals, so now I go over on my scratch paper and I go subtract that is 8, 3 subtract 1 is 2, equals 0.2837 volts. Okay? And that answers
Why is it
question
written like that?
B. What?
Why is it written CR3 plus to CR2 plus when in the actual equation it goes CR2 plus and then products is CR3 plus?
Because reduction potentials, well, in this notation, I have the oxidized form first and the reduced form second. It's written as a reduction. Okay? The oxidized form, reduced form. Same here. Oxidized form, lead plus 2, going to lead. So when I write the reduction potentials with this particular notation, it is the oxidized form followed by the reduced form. Okay? Did that answer it? Did everybody get that question? Now, he asked about the notation, why the oxidized, why the okay, now, part C, which is okay. So this is, again, a little bit wordy, but it's pretty straightforward. What do I'm going to need to use what name equation to solve this? The Nernst Equation, which gives us the cell voltage under non-standard conditions, which I'll spare you the derivation of it, but you should be able to, for your own amusement, derive.
Extra credit?
No. We've got to have how many pages? Save us a tree here. The extra credit's going to take up some space. Okay, now, we'll just go under at 25 degrees Celsius. The Nernst equation takes on the following form. Okay? In other words, it's going to be the standard, the cell potential under standard conditions minus 0.0592 volts. And it was because this is, actually it'd be minus RT over NF, where F is a Faraday and R is the gas constant times the temperature. And this is the log of, and it'd be the natural log of Q. And so we absorb the 2.303 times RT and divided by a Faraday, and we got 0.0592 volts. So this is the most convenient form of this expression, particularly when it comes to calculation. So all we need to solve this, since we already know the cell potential under standard conditions, is Q. What's Q represent in this particular expression?
Mass action.
Well, yeah, or actually we call it the reaction quotient. So Q depends on the conditions and the context which it's used. And let's see what Q is. Well, all we need to do is Q is equal to what? Look at the expression up there. The concentration of chromium 3+, the anodic ion, and that is
Do we put
Squared.
that squared in there?
oh, absolutely. Why?
Just like that step of the thing. There's 2 moles in it.
Yeah.
Those stoichiometric?
Because the stoichiometric coefficients. Exactly. And that's divided by the reactants, which are lead 2+ and chromium 2+. Again, squared.
Dr. Fletcher, you can square in your key, just so you know.
I didn't?
No.
Okay, that was another typo.
Yeah.
Thank you for bringing that to everybody's attention. Now, why didn't the lead occur, the solid lead occur in the mass action expression?
Unit activity of 1.
Yeah, it's a solid, and solids have unit activity. They're equal to 1. So it doesn't have any impact on the resulting expression, because multiply and divide by 1 all day. It doesn't change it. And so I'm going to go and write this in exponential form. This really becomes much more easily calculated. So chromium 3+ is 10 to the what? 10 to the minus 1. So I have 10 to the minus 1 squared over, and the lead 2+ is 10 to the minus what?
4.
10 to the minus 4 times 10 to the minus 2. 10 to the minus 2 squared. And that's pretty straightforward. So what do I do? What do the rules of exponents do here? I multiply, so minus 1 times 2 is 10 to the minus 2. 10 to the minus 2 times 2 is 10 to the minus 4. 10 to the minus 4. What do I do when I multiply 10 to the minus 4 times 10 to the minus 4? I add. So I end up with equals 10 to the minus 2 divided by 10 to the what?
Minus 8.
Minus 8. And that is equal to, what is 10 to the minus, what do the rules of exponents have me do here?
10 to the 6.
10 to the 6.
I subtract. Right?
Yes.
Okay. So 10 to the minus 2 minus a minus 8 equals 10 to the 6. And just to round off the day, what is the log of 10 to the 6?
6.
It's not 6.
Thank you very much. And so E cell is equal to E naught cell, which we found was something. 0.2837 minus 0.0592 volts divided by, and what? How many moles of electrons are transferred in this process?
2.
Divided by 2, and that is times the log of 10 to the 6th, which is, well, I can go ahead, since we've already, well, no, let's include that. So we can write it out one more time. That just feels so good. Okay. So, although this is going to be 6, 6 divided by 2 is what? And so I'm going to multiply 3 times 0.0592 over on my scratch paper. 9 times 3 is 27. 5 times 3 is 15, 17. Okay, so that is going to be subtracted from 0.2382837. So 0.2837 minus 0.1776. 1.
Oh, it's the number.
And 13 subtract 7 is 6. And that's a 0. And that's a 1. Okay, equals 0.1061 volts. Which is probably not what I had on the key because of the typos.
No.
Is that what I had on the key?
No, it's there.
I did it right?
Yeah, there's one.
I'm shocked.
You fixed it when you did the actual problem.
I fixed it when I actually did the problem. I just didn't write it out right. Okay. Okay. So this one is guaranteed on the test. We need an electrolytic cell. We need a galvanic cell. And so we've got them. And this is Nernst equation. Now, the last, I think, calculation problems we have, we've pretty much done them all except 13 and 14. So I always like to save the best for last. It makes it more fun. Okay, I'm going to move over to this board. Okay. Number 13.
Is there any time Boltzmann's really like more efficient?
Boltzmann's, you mean Boltzmann's approach versus Carnot's approach? That's a good question. I would say it's more efficient or effective from conceptual point of view. There's Carnot's was based on experimental results. And it actually wasn't, Carnot didn't know the second law. It was Rudolf Clausius's use of Carnot's results. And Carnot just studied the efficiency, Sadie Carnot studied the efficiency of heat engines. And was driven to find the maximum efficiency. And the maximum efficiency is going to occur with what kind of process, now that you bring it up? With a truly reversible process. And there is no such thing as a truly reversible process, which is easy for me to tell you, but he had to tell Napoleon when he was told to come up with a more efficient way of getting his stuff, you know. And the good news was Napoleon was enough of an engineer to not shoot him, okay, because he wasn't known for his great sense of humor. So you think your job is tough, no matter what your job is. Sadie Carnot had a tougher one, in my opinion. But he was trying to find the maximum efficiency. And let's just recant or recoup our derivation of Carnot's results. Why was he looking for the maximum? He was looking for the maximum what out of a process?
Available work.
Maximum available work. And for every cycle, for a true cycle, the Q in the cycle, the heat in a total cycle, is because the Q and the work are not state functions, and so for every cycle, the state functions like energy are equal to 0 because they are path independent. And since the state function is equal to 0, the Q for a reversible process, and the first law tells us the delta E is equal to Q plus W. Just to real quickly recoup this. Q plus W, and Q plus W had to be equal to 0. Therefore, Q reversible, and it turns out the maximum work is done in a reversible process, which is when we have how many stages? Infinite number of stages. Okay, and frictionless. And all he found out was that there is friction. There is no truly reversible process that can be designed. And so there's no perpetual motion. And so he was looking for the maximum work was going to be available for the process that contained the maximum heat. And therefore it turned out that the difference between the hot stage and the cold stage was going to give the maximum heat and give the greatest efficiency. And that's where he came up with what appeared to be a new state function, although he didn't know it. And that was, he found that the heat transferred in the hot stage divided by the temperature at which that hot stage, the transfer of heat occurred, plus the heat transferred in the cold stage divided by the temperature in the cold stage, turned out to be equal to 0. Okay? And that meant that there was some sort of a new state function which was Q over T, but it was Q reversible over T. And that's Carnot's approach to entropy. And it was Rudolf Clausius that actually, and Lord Kelvin, I guess, don't want to leave the Brits out. Clausius representing the German interest, and Carnot obviously representing the French. As always, driven by the need to kill each other more efficiently and effectively, which has motivated people for a long time. Now, consider, so number 13, consider the isothermal expansion or compression, my bad. I'm going to learn to read sometime.
By the end of the semester.
Yes. Well, in my continuing education, of 3 moles of an ideal gas from the Gesundheit. Of 4 liters to a final of 1 liter. Again, it probably took me longer to write the thing than it's going to take us to solve it. And there you can take either approach. Trevor was asking which one's most, or Chris, was it Chris that you were asking which one's more efficient? Interesting play on words there, because Carnot was studying efficiency. So I'll start with that approach. And what do we know about the Carnot approach? Carnot showed that delta S, so this is Carnot's. Okay, what did Carnot give us? Delta S for such an isothermal
Number of moles.
is equal to N
R times R times natural log.
Well, this certainly does look awfully simple, doesn't it?
Yeah.
So this is going to be equal to, what is N?
3.
R, natural log of
1 over 4.
1 over 4, which is, I can say is 4 to the minus 1, and I can pull that minus 1. What can I do with the rules of exponents? Let me do. Equals minus 3r natural log of 4. And that is a sufficient answer. So that is smooth and simple. And, okay, since Carnot studied efficiency, I would give you that answer. Yeah, this is probably the more efficient. But, and it's not a trivial but. However, the Boltzmann, what?
I've been studying both this whole time.
Well, the Boltzmann,
I'll do 2 of them.
I'm going to do the Boltzmann. Please, please, relax. No, the Boltzmann is the most revealing.
Yeah.
Carnot's was basically the expression of experimental empirical results. It was Ludwig Boltzmann who came up with a theoretical explanation which gave us, among other things, the kinetic molecular theory of matter, without which we pretty much wouldn't have much of a class for the last year or so. Chemistry. And thermodynamics and such. And regrettably, because, like I said at the beginning, there is no such thing as authority in a scientific sense vested in any individual. It is indeed vested in first principles. First principles are both your weapon with which you reveal fraud in somebody's efforts. It is also your armor. It provides you a foundation. So it rests upon the sound first principle foundation upon which you base what you're talking about. And Boltzmann did a beautiful job. But unfortunately at the time, what I just said sounds nice, and it's in fact true. But in practice, it happens periodically, and it happens all the time because of human nature. Authority was vested in a guy by the name of Wilhelm Ostwald and his buddy Mach. And they didn't like Boltzmann's theory because they hadn't come up with it. And so, essentially, they just kept beating the guy down, and he ended up committing suicide. And physical chemistry ceased to be for 50 years. It wasn't until World War II, when all those guys died off, that physical chemistry came back into existence as an actual, authentic, scientific field of study. And were it not for the efforts of the organic chemist who accepted molecules 50 years earlier, we would be way back. So the physical chemists were able to steal it back from the organic chemist around World War II, after World War II. So this sort of thing happens all the time. Now, enough history. Now, Boltzmann's approach. So Boltzmann's approach is that S is equal to what? KV natural log of omega, and therefore delta S is equal to KV natural log of omega final over omega initial. And then we're going to go through and write that this is, so delta S is equal to KB, which turns out to be, what is KB again?
R over N naught.
R over N naught, where N naught's Avogadro's number, times the natural log, and the final system is CV, C being some sort of constant, proportional to the volume, and over 4 CV, and it is how many moles?
3.
So it's 3 in naught. So it turns out, and that's what's so revealed, that was what was revealed, Boltzmann took essentially a statistical approach, and the big profound thing he was saying, which is something that could not, which is what Ostwald could not accept, was the most likely thing that's going to happen is the most likely thing that's going to happen, which is hard to accept. I mean, I agree. It's just tough. Who could imagine such an outlandish statement? So notice that the CV drops out, this constant times the volume, and so this I can then pull the 3 n naught through, and it's going to be equal to 3 n naught times R over n naught times the natural log of 4 to the minus 1, which I can then take care of in 2 steps. First, Avogadro's number drops out, and I end up with, and I can pull the minus sign through, equals minus 3R natural log of 4, which agrees with Boltzmann. I mean, with Carnot.
We can choose either one.
You can choose either one, and to answer Chris's point, yeah, I think this one's a little bit easier, but to address your apprehension, Boltzmann was by far the more revealing, and what we're after here is comprehension. So I want you to understand this, and I'll take either one for an acceptable answer. Okay, now, last on our hit parade is number 14, and that is an ideal monoatomic gas. That was what it is. I better write it down. Should I go over to this board? So I can, yeah, I'll go over to this board. Let me erase so I have a board to go to.
Maybe we should skip writing out the question this time.
Oh, the only reason I'm writing out the questions is so that the folks who are viewing this who aren't here have a more of a standalone review. Regrettably, this is late in the day, so they have to filter through to get to this problem. But it's there for them. Okay. So this is for our colleagues who could not make it to this session. And hopefully I have answered questions that you have. Okay. Now, an ideal monoatomic gas at 3 atmospheres in a 30-liter volume is transformed to a state with 1.0 atmospheres and 10-liter volume. Here. What is delta E for the process? And I say recall that heat capacity at constant pressure for a monatomic ideal gas is equal to 5 halves R and CV is equal to 3/2 R for a monoatomic ideal gas. And okay, and I even included that PV equals nRT, which
When did we learn that?
you probably already knew that. I just threw it in there because I don't know. I felt like I shouldn't need to include that, but it just for laughs. Okay. Now notice I didn't say anything about the pathway. So you have all the choice in the world. We're looking at if this is pressure going this way, and this is on scratch paper. I'm going from 3 atmospheres. 1, 2, 3 atmospheres down to 1 atmosphere, and I've got 10 liters. This is volume going this way. 20 liters, and how many liters? Oh, 30 liters. Okay, and so I'm starting out at 3 atmospheres and 30 liters, which would be here. And I want to end up with 1 atmospheres and 10 liters here. So this is A, and this is B. I'm starting here, I want to go there. I can choose any path I like.
Straight line.
Well, that would be probably the most difficult of all possible paths to solve. Usually what you want to do, what do I want to do in this? I want to take what type of steps? Iso-happy steps or isobaric and isochroic. And an isobaric means constant pressure. So I could go in an isobaric, let's follow this path. Let's take it this way. In an isobaric step, that means constant pressure. And then at constant volume, at an isochroic step. I could have done an isochroic step first and then an isobaric step. It's going to give me the same result either way, right? Okay, because this has to do with the energy being a what kind of function? State function. Therefore, it is path independent. Okay, so let's try it this way. So Q, let's call this, I'll call this step C, or state C. So Q, A, C, B equals Q, A, C plus Q, C, B. And that's equal to, and we can cut right to the chase. I'm going to save you all that derivation because we've already done this before. And what is AC? It's an isobaric, therefore it's going to be ultimately 5/2. What is the pressure? Times 3 atmospheres. And what is delta V? Negative 20 liters. And that plus, and I'm running out of room. Can you get this? Oh, you got it.
Yep.
Plus, and now for the isochroic step, the heat is going to be equal to 3/2. What is delta P? Negative 2 atmospheres. And what's the volume? 10 liters. Okay, and so that's equal to, now let's do the math. 20 divided by 2 is 10. 10 times 3 is 30, and 30 times 5 is, so that's minus 150. liter atmospheres. And then what's the second step? Okay, 2 divided by 2 is 1, and 3 times 10 is 30, so that's going to be minus 30 liter atmospheres equals minus 180 liter atmospheres. And now W, A, C, B is equal to, what is WAC? Minus P A C times delta V A C equals what? What's the pressure? Minus 3 atmospheres times, what's delta V again?
Negative 20.
Negative 20 liters equals plus 60 liter atmospheres. And because WCB is what? 0. Because the volume doesn't change. Okay. So delta E is equal to Q plus W equals minus 180 liter atmospheres plus 60 liter atmospheres equals minus 120 liter atmospheres. And that would be, you don't need to include this diagram. This is on scratch paper. This is what you would have. Okay? And you can go back over the first midterm for the real details there in case it's been a while, since this is what we started the semester off with. Okay? But that pretty much covers all the written problems. Now, if you guys want to, we can talk some more.
Take 5.
You guys ready to take 5, or you want to talk about the multiple choice, or just take? You want to take 5 or call it a night?
Take 5.
Take 5.
Take 5?
Let's complete the recitation. When we started.
Okay.
Potential fucking
Okay. Let's take 5.